Again, welcome to Operating System CS332 class. This lectures cover the process description and control, which is chapter 3 of our course textbook. So again, in order for operating system to manage process and resources, it must have information about the current status of each process and also resource. So again, in order for operating system to manage any resources in a computer system, the operating system must have information about that resources. So the universal approach to providing this information is straightforward. The operating system constructs and also maintain the tables of information about each entity that is managing or each resources that is managing. The general idea of this scope is shown here in this diagram, and that's our main focus in these lectures. And we shall go through what is memory tables, I/O tables, file tables, and also the process tables. So those are the four major resources that the operating system manages. So it must have information of all these resources. So again, there are four different types of tables that is maintained by the operating system. As we said, the memory table, the I/O table, files, and the process. Although the detail will differ from one operating system to another, but fundamentally, again, every operating system maintains information in these four categories. So first, we start with the memory tables. So memory tables are used to keep track of both the main memory and also the secondary memory. The secondary memory will be our virtual memory, which will be another topic we are going to cover in the future. For example, the concept of paging and segmentation and how we translate logical memory address to physical memory address, etc. So some of the main memory is reserved for the use by the operating system. And then the remainder is available for use by the processes. So processes are maintained on a secondary memory using some sort of virtual memory or simple swapping mechanism. The memory tables must include the following four items or the four informations here. First is the allocation of main memory to process. What must have this information. Also, allocation of secondary memory to process. And also any protection attributes of blocks of main memory or virtual memory, such as which process may access certain shared memory regions. Now, any information that's also needed to manage the virtual memory. And we are going to examine again the information structure for main memory management in the future lectures. So next is the input-output tables or the I/O tables. So the I/O tables also are used by the operating system to manage the I/O devices and also the channels of the computer system. So at any given time, an I/O device may be available or assigned to a particular process. If an I/O operation is in progress, then the operating system needs to know the status of the I/O operation and also the location in main memory being used as the source or the destination of the I/O transfer. And also I/O management, we are going to examine that in our future lectures also. The next is the file tables. So again, the operating system also maintains file tables. These tables provide information about the existence of files, their locations on secondary memory, their current status, and other attributes. Much, if not all, of this information may be maintained and used by the file management system. in which case the operating system has little or no knowledge of files. In other operating system, much of the details of file management is managed by the operating system itself. And also we are going to cover this topic in detail in our future lectures when we cover the I/O devices. Next is the process table. Also, the process table must maintain by the operating system. So the operating system must maintain a process table in order to manage the processes. And the remainder of this section is devoted to an examination of the required process tables. So again, our chapter 3 concept, we are covering process. So we may go, in these lectures, we may go more detail in process tables. About the memory tables, I/O tables, we may cover that more detail when we start memory management topic, and also the I/O devices and topics. So again, before proceeding to this discussion, 2 additional points will be made. First, we show the 4 distinct set of tables in our previous diagram. That's from the memory, I/O, files, and process. One thing that it should be clear that these tables must link or cross-examine or cross-reference in some fashion. Because again, memory, the I/O, and files are managed on behalf of process. In order for a process to be working, it may need a memory. Also, it may need some I/O features such as files, etc. So this all must be linked. So again, there must be some references to these resources directly or indirectly in the process table. So again, we have one process, we may have information about the resources that the process is using. So example can be the memory resources, the address, or the data I/O items. So these files referred to in the file tables are accessible through an I/O device, and also will at some time be in a main memory, or at least in the virtual memory. So the table themselves must be accessible by operating system and therefore are subject to main memory. Now, secondly, how does the operating system know to create the tables in the first place? Clearly, the operating system must have some knowledge of the basic environment, such as how much main memory exists, what are the I/O devices, or what are the identifiers, and so on. So this is an issue of configurations. That is, when the operating system is initialized, it must have access to some configuration data that define the basic environment. And this data must be created outside the operating system with human assistance or by some auto configuration software. So next is the process control structure. Now we should consider what the operating system must know if it is to manage and control a process. First, it must know where the process is located. And secondly, it must know the attributes of the process that are necessary for its management. So the attributes will be such as process ID or the process state, etc. So again, to manage and control a process, the operating system must know where the process is located, the location. Also, what are the attributes of the process, such as the process ID, process state, and the memory address where the process is located, etc. So next is the process control structure. We talk about the process location and also the process attributes are the 2 major information that, again, the operating system need in order to manage the operating system. So again, before we can deal with the questions of where a process is located or what is its attributes, first we need to address an even more fundamental questions. Example would be, what is the physical manifestation of a process? Again, what is the physical manifestation of a process? So at a minimum, a process must include a program or a set of programs to be executed. And as we mentioned earlier, the definition of a process is a program in execution, a program that is running. When a program is not running, it's called a program. When it's running, again, it's called a process. So a process must have at least some resources, including, most important, the memory address. And each process may have its unique ID card with an ID number, which is assigned by the operating system. So associated with these programs is a set of data location for local and also global variables and any defined constants. Thus, a process will consist of at least sufficient memory to hold the programs and the data of that process. In addition, also, the execution of a program typically involves a stack that is used to keep track of a procedural calls and also the parameter passing between procedures. And so finally, each process has associated with a number of attributes that are used by the operating system for process control. So the location of a process image would depend on the memory management scheme being used. And also in the simplest case, a process image is maintained as a contiguous or continuous block of memory. And this block is maintained in secondary memory, usually in a disk, so that the operating system can manage the process. At least a small portion of its image must be maintained in main memory. Also, to execute the process, the entire process image must be loaded into the main memory, or at least the virtual memory. So the operating system needs to know the location of each process on disk, and also for each such process that is in the main memory. The location of that process in main memory. Again, we know a slightly more complex variation on this scheme with the CTSS operating system. And we discussed this in chapter 2, that with CTSS, when a process is swiped out, part of the process image may remain in the main memory. So the operating system must keep track of which portion of the image of each process are still in main memory. But again, we know modern operating system presume paging hardware that allows non-contiguous physical memory to support partial resident process. We may discuss this more detail again when we cover the memory management topic. So these are some of the typical elements of a process image. We have the user, again, data. And we also have the user program. We have the stack. And also we have the process control block. So the user data will be the modifiable part of the user space. This may include program data, a user stack area, and programs that may be modified. And the user program, again, will be the program to be executed. And with the stack, each process has one or more last in, first out stack associated with it. Each process has at least one or more LIFO, last in, first out stack associated with it. So a stack is used to store parameters and also the calling address for procedure and system calls. Also the process control block, data normally is needed by the operating system to control the process. So next is the process identification. So the identifiers can be numeric identifiers that may store with the process control block. Example may be the identifier of this process, also identifier of the process that created this process. That would be the parent process, and also user identifier. We also have the process state information. First is the user visible registers. Then we also have the control and status registers, and also the stack pointers. So again, a very sophisticated multi-programming system will require a great deal of information about each process. And as we explained, this information can be considered to reside in a process control block. Now, different systems will organize this information in different ways. And several examples of this appears at the end of these lectures. So for now, let us simply explore the type of information that might be of use to an operating system without considering in any detail how that information is organized. So those are the possible informations. So the table here will list a typical category of information required by operating system for each process. In example, as we mentioned, we may have the categories of like process identification, process state information, and also the process control attributes. So process state information can be user visible registers. Here we say the user visible registers is one that may reference by means of machine language that the processor executes while it's in the user mode. Typically, there are from 8 to 32 of these registers, although some RISC implementation have over 100. We also have the control and status register. These are a variety of process registers that are employed to control the operation of the processor. So this will include the program counter. As we know, program counter always point to the next instruction that must be executed by the CPU. We also have the condition codes. This may result of the most recent arithmetic or logical operations. Then we have the status information. This also include the interrupt, enable, or disable flags, etc. So again, we also have the scheduling and state information, data structuring, inter-process communication, process privileges, memory management, and also resources ownership and utilization. These are all typical elements of a process control block. So again, as we mentioned, a sophisticated programming, multi-programming system require a great deal of information about each process. And also, as we explained, this information can be considered to reside in a process control block. So next is the process identification. Now, with respect to process identification, in virtually all operating systems, each process is assigned a unique ID number or numerical identifier, which may simply be an index into a primary process table. Otherwise, there must be a mapping that allows the operating system to locate the appropriate tables based on the process identifier. And this identifier is useful in several ways. Many of the other tables controlled by the operating system may use process identifiers to cross-reference process tables. So for example, the memory tables may be organized so as to provide a map of main memory with an indication of which process is assigned to each region. Now, similar references will appear in I/O and also the file tables. When processes communicate with one another, the process identifier informs the operating system of the destination of a particular communication. Now, when a process is allowed to create other process, identifiers indicate the parent and also the descendants of each process. In addition to these process identifiers, the process also may assign a user identifier that indicates the user responsible for the job. So again, when the process are allowed to create other process, identifiers indicate the parent and also the descendants of each process. Now, next is the process state information. Now, normally the process state information consists of a content of a process registers. While a process is running, of course, the information is in the registers. When a process interrupted, all of this register information must be saved so that it can be restored when the process resumes execution. Now, the nature and also the number of registers involved depend on the design of the process. And typically, the register set will include user visible registers, also control and status registers and stack pointers. And we discussed this again in our lectures in chapter 1 already. So next is again the process control information. Of particular note, again, all process design include a register or a set of registers, often known as the program status word, PSW, that contains the status information. The PSW typically contain a condition codes plus other status information. So a good example of a processor status word is that on Intel 86 processors, which is referred to as the EFLAGS registers. Now, the third major category of information in the process control block can be called, for want of a better name, which is again the process control information. This is again additional information needed by the operating system to control and also coordinate the various active processes. And this is the last part of the table in our previous slide, which indicates the scope of this information. Again, as we examine the detail of operating system functionality in succeeding lectures, the need for the various items on this list will be very clear, or will become clear. So the next diagram here again shows or suggests the structure of a process image in virtual memory. So we can see process 1, process 2, etc. up to process N. And each process image consists of a process control block. So this process control block, also we have the user stack, we have the private address space of the process, and also other address space that the process share with other processes. So in this diagram again, each process image appears as a contiguous range of addresses. But in actual implementation, this may not be the case. It will depend on the memory management scheme and also the way in which control structures are organized by the operating system. So again, here we have different processor. One have is a process identification, the process state information, process control information, the user stack, private user address space, and also share address space. Now, what is the role of a process control block? Now, the process control block is the most important data structure in an operating system because each process control block contains all the information about the process. And also we should know process is the major task in the computer system. Again, as we said earlier, a process is a program that is running, executing, performing some task. So the blocks are read and or they are modified by virtually every module in the operating system, including those involved with the scheduling, resource allocation, interrupt processing, and also performance monitoring and analysis. So here one can say that the set of process control blocks or the set of a process control blocks define the state of the operating system. So this brings up an important design issues. So a number of routines within the operating system will need access to information in process control blocks. Also, the provisions of direct access to these tables is not difficult. Each process is equipped with a unique ID, and this can be used as an index into a table of pointers to the process control blocks. Now, the difficulty is not access, but rather protection. Again, the difficulty is not about accessing, but protection, rather protection. So two problems present themselves here. A bug in a single routine, such as interrupt handler, could damage process control blocks, which could destroy the system ability to manage the affected process. Also, a design change in the structure or semantics of the process control could affect the number of modules in operating systems. So these problems, again, can be addressed by requiring all routines in the operating system to go through handler routine, the only job of which is to protect process control blocks, and also which is the sole arbiter for reading and writing these blocks. We may have a trade-off in the use of such routine, which involve performance issues and the degree to which the remainder of the system software can be trusted to be correct. So here we have the mode of execution. We have the user mode, which is the less privileged. When we say a less privileged mode, means when the process is being executed on a user mode, it doesn't have access to the computer resources such as the main memory. So it's less privileged, but user mode will be the most safe mode. It's the safe mode. System mode is more privileged because the process have access to almost all the computer resources, but this is not a safe mode. So again, before we continue with this discussion, we should know one thing, the operating system, the discussion of in which the operating system manage process, we need to distinguish between the mode of process execution normally associated with the operating system that are normally associated with user programs also. So as we said, most of process support at least two modes of execution, either the user mode or the system mode. So certain instructions can only be executed in the more privileged mode, which is again the system mode. This will include reading or altering a control structure, such as the program status word, primitive I/O instructions, and instruction that are related to main memory. Now, the less privileged mode is often referred to as the user mode because user programs typically will execute in this mode. So the more privileged mode is referred to as a system mode, control mode, or kernel mode. So this is a typical table showing the function of an operating system kernel. We have the process management, which is main function for process management, process creation and termination, process scheduling and dispatching, process switching, also process synchronization and support for inter-process communication, and also management of process control blocks. In our next lectures, we may go detail more about this section. Then also memory management, allocation of address space to process, swapping, paging, and segmentation management. We'll get details in this when we cover the main memory management and also virtual memory concept. Then I/O management, the buffer management, allocation of I/O channels and devices to process. Then support function can be interrupt handling, accounting, and monitoring. Again, we are going to cover most of all these concepts in our future lectures. So we're going to end our lecture here. Again, our main goal in these lectures is to understand the concept of process control block, different types of resources, or how the operating system again manages the process and resources. And in order to manage the process and the resources or any resources by the operating system must know the informations of all the process and resources. And by knowing this information, it creates the tables which we discuss in this lecture. So we should know again, there are 4 major categories of different tables, which again, we cover in this lecture. So again, wish everybody the best and thank you for your time.